Hello. How are you all doing? I didn't really see any of you answer out loud, but I'm fussing with my little device here to try and get it to work right. Hmm. Oh, here we go. Perfect. Okay. So let's think. I'm feeling a little bit better, meaning I can be upright now. And I've had enough medication of the right sort that my nose isn't running the whole time, but I still have chills and my head is doing loops. So I apologize in advance if anything I say is not quite right. Just ask for a clarifying question. I think it's always best to start with questions that you have related to course material before we move forward with anything new. And I'm hoping one of you will unmute at least so I can check the volume on my speakers. Or ask
Yeah.
a question. Perfect.
Hello, Professor. I have a question about the lab.
Yeah.
Um, there was a part under the normal distribution that said
Yeah.
to find some chart in the textbook, but when I went to the pages, um, it didn't look like the right chart.
Okay. It could be that the copy of the textbook that you have is a little bit different than the one I used for creating the lab. I will draw your attention to, let me share a screen. Boom. So hopefully you can see in front of you now uh, Canvas for this class. The
Hmm.
normal table probably is the one that I was drawing your attention to, and it gives cap phi, the cap phi function for any particular value of z. So you give me an input like a z of negative, say 3.51, and you would look negative 3.5, and then the column one. So it says the lower tail area is 0.0002, that lower tail area 0002. Now, page 582 is what I thought, well, where it appears in the copy of the book that I used. I don't know if that's the one I referred to, but this is where you could find it in that Z table portion of Canvas. Does that
Okay.
make sense, Jake?
Yeah, I saw that table and figured maybe that's what you were referring to,
Yeah,
but I just wanted to double check.
yeah, definitely. And the JMP probability distribution calculator, did you use that yesterday also?
Yes.
Okay. I find that that is fairly helpful, okay, for tackling these problems. I actually find the normal table or the T table, the chi-square table, I'm pretty good at that because I was trained to use that years and years and years ago. But most students find that probability distribution calculator is really quick and they end up preferring that. Any other questions? Okay, so as far as I know, there's three things administratively that I want to mention. One of them is any homework that was due yesterday by midnight is due today by midnight. Now is your chance to ask questions about those homework problems. Two is same deal for the lab that you should have already completed. Yeah, I get it. If you do turn it in, that's wonderful. And I don't know that I saw anyone having turned it in. It might be because I changed the lab due date. Have any of you turned the lab in? This is the give and take. You answer back or do a thumbs up or something. Have any of you turned the lab in? Okay. So the key on that lab is if you turn it in, that would be good. Especially for those of you, this is getting to point number 3. Those of you who want to formally add the class, I can give you permission numbers to add the class as soon as you've turned that lab in. So just make sure you guys get it done promptly, and there should be nothing holding you back from getting that done by, well, let's just say noon yesterday, because it was only involving material that sort of was related to that first day of class. And so doing that very, very promptly would be a good thing. And so the last thing I'd mention is if you already filled out that form to say, yes, I still want to add the class, etc. If you follow up with an email saying, okay, I've turned in everything, including the lab, and I still want to be in the class, then I'll email you out those permission numbers in order according to the waiting list for the class. Okay. Any questions, last questions about administrative or other matter? Okay, so what I'd love to do is to dive in on some material in chapter 1, section 6 now. Okay. And in chapter 1, section 6, let me just move over here. We're talking about some commonly used distributions and commonly used discrete distributions in particular. And so maybe talking about the 2 that are the 3 that are the most famous. Bernoulli, binomial, and then Poisson. Actually, Bernoulli, let's just skip that. Let's go right into binomial because it's the binomial case includes Bernoulli is one special case of binomial. Okay, so the binomial distribution. And I'll just describe a situation, and then we'll note that that is indeed defining binomial. So suppose you're going to perform an experiment, okay? And you're going to do that experiment a fixed number, n times. So n trials. And if each outcome of the experiment is either a success or a failure, and all of the outcomes have the same chance of success, and furthermore, you have independence of the trials. Let's be clear about that last one. Independence of the trials. It's sort of like flipping a coin. If I tell you the first outcome of a coin flip was a head, does that give you any information about the result of the second coin flip? The one that has yet to occur? No. In some situations, there's a lack of independence, but usually not with coins. Let's try cards in a deck. And I'm talking, 52 card deck of cards, and there's 4 aces. If I pull one card off the top of the deck, and it's an ace, does the chance that the second card drawn change? Does the chance that it's an ace change? Well, because the first card was an ace, the second card is now less likely to be an ace because there's only 3 aces in the remaining 51 cards. Cards are not independent, dice and coins are. Okay, so if we have a situation like this and you ask yourself, okay, well, is this a situation you could go through the checklist. Am I trying something a fixed number of times? Okay. Are there only 2 possible outcomes? Now, some people say, oh, well, with a die, there's 6 possible outcomes. You might be interested in something like getting a 5 or not a 5, or 2 possible outcomes. And on dice, okay, the chance is the same for every trial, and there is no changing of the chances based on earlier outcomes. If you have a situation like this, then if X is equal to the number of successes we say that X is distributed binomial with n trials, where P is the chance of success on any given trial. Okay, again, you go through the 1, 2, 3, 4 checks, and if you say, oh, we've hit all of those, and if you're only keeping track of the number of successes, successes we say follows a binomial distribution. Okay, so let's try an example, okay? And let's take a screenshot of this so I can move forward. Supposing we're going to roll a die 5 times, so n is 5 rolls of the die, and if there's a 1 in 6 chance as the chance of getting a 3 on the die, okay, so we're talking the chance of the 3, what is the probability of getting 4 3s in the 5 rolls? Probability of x equal 4. Okay, so I want to know what's the chance of 4 3s in 5 rolls. Okay, so with binomial probability distribution, we would say the probability that the random variable x, the number of 3s, is any particular value that's a lowercase x, that's just n factorial over x factorial, n minus x factorial, and then we're going to multiply that by p raised to the power x, and then 1 minus p to the chance n minus x. So this just gives us the probability of exactly lowercase x successes. So we want to know what's the chance of 4. Okay, let's change colors here and go ahead and do the work. So the probability that the random variable, the number of 3s in 5 rolls, what's the chance that we get exactly 4 3s in 5 rolls? That's going to be 5 rolls factorial over 4, 4 factorial, and then 5 minus 4 factorial times then the chance of getting a 3, 1/6 raised to the power of 4 times 1 minus 1/6 to the power of 5 minus 4. Now, this is a situation where I can probably do a little bit of the work, and you could all be very helpful for me. This is going to be 5 because the 5, 4, 3, 2, 1 in the numerator, 4, 3, 2, 1, that's going to cancel out, and 5 minus 4 is just going to be 1, but 1 factorial is just 1, so we get 5 times 1/6 to the 4th times 5/6. And I don't know the value of that off the top of my head, but if one of you has the number off the top of your head, I would love to know its value.
It's a 0.003.
0.003. Now, you rounded at the thousandths place, which is cool. Usually, for small numbers like this, I would probably round at the 10,000ths place. I'm not asking you to do that right now, but typically when you see very, very small numbers close to 0, or very, very large numbers quite close to 1, in probability, a little bit more precision is a helpful thing. Okay, so I'm happy with this answer. Any questions about how to figure out something that's binomial like this? Okay, so let's screenshot there. Let's give you another example of binomial. Go. It's a good binomial example. Okay, suppose we have a, geez. total brain fart day. When your head is spinning, okay, so what's something that a person could do? Okay, so shooting a basketball. Okay, so free throw shots. By the time one hits college, okay, as a collegiate athlete, free throw shots, they're pretty much as good as binomial. You walk up to the line, you do your thing, whether it's bouncing the ball once or 3 times, whatever. You do the same thing every time. You're trained exactly to do it every single time the same. So the question is the number of points that you score across 10 consecutive free throws, is that binomial or not? So let's consider the question. So is n, the number of trials, fixed? Are we just doing the 10 shots? Yeah, so n is fixed. Is it a success or a failure? Well, I guess either you score a point or you don't on any given shot. Okay, so that's good. Third, is the probability of success always fixed? And this is where people will argue sometimes. They'll say, well, you know, if like when Duke plays basketball, they have the people behind who wave, you know. I'll just say I have seen no evidence to suggest for any particular player in college basketball that there is a way of saying, aha, you have a lower chance of success now or a higher chance of success now. So I'm willing to believe this, but I'm going to sort of put a little question mark next to it, because I'm not saying for sure it's true. I'm just saying I've seen several studies where they look into the question of whether college and pro basketball players have an identical chance of success, whatever the situation is. They practice. They have about the same chance of success, if not exactly. And then the fourth one is independence. And this is one where maybe talking sports for a little bit is going to be helpful. I'm going to say in basketball free throws, again, evidence that says, you know, looking for whether their one shot impacts the player's chance of making the next one. There is no evidence to suggest that that is the case. Now, this is a little bit different than pitchers in baseball. Pitchers in baseball, when you throw the ball over the plate, sometimes pitchers can, quote, get in their head, and they have a difficult time delivering strikes compared to what they had been doing earlier in the season. I don't think pitchers are independent of each other. If you get in a funk, you might, and pitches are independent of each other. If you get in a funk, you might then very well be throwing the ball poorly for a period of time. Okay, but that's a very different situation than shooting a basketball from the free throw line. And again, looking at several studies designed to detect a lack of independence. Like, does the player, if they've had 5 in a row correct, you know, get the previous 5 free throws, if they got the previous 5 versus if they only got 3 of the previous 5, there's no difference in the rate of success that we've been able to spot. So I'm willing to, again, call this a success. So I'll say check, but then that is, hold on. I'll say, yeah, check. We've hit this condition, but again, this is based on only empirical evidence, not telling us that this is wrong. Okay. So if the player normally shoots a 80%, okay, what is the probability that that player gets exactly 8 out of 10 in a row? So n is 10. So you tell me n and p, and then the chance you want to solve for. It's a matter of plug and chug. Okay, so the probability of exactly x, the number of free throws that are made, the chance that that's exactly 8 would be a 10 factorial. No, hold on a second. 10 factorial over 8 factorial, then 10 minus 8 factorial times then 80% is the chance of success to the 8th power, 1 minus 0.8 to the 10 minus 8. And I'm going to write this down in a different color downstairs with a little bit of simplification. This is just 10 times 9 over 2 times 0.8 to the 8th power times 0.2 squared. And I don't know the number, but I'm betting that one of you can tell me the number relatively quickly.
I got 30.199. Like, okay, 30.2.
Okay, so 30.2%.
Yeah.
So yeah, if there's a player who normally shoots at an 80% rate, okay, and they're going to take 10 free throws in a game, okay, what's the chance that they get 8 out of 10 really close to their typical rate? There's a pretty good chance. Okay, binomial. There are a couple situations that aren't binomial that sound almost like binomial. So let's mention one of those. There's something called well, okay, let's not go with her. If you don't have the number of trials fixed in advance, that is not binomial. So if you hear anything like, oh, we're going to try sampling until we hit a success, or we're going to sample until we hit 2 successes, or we're going to sample until we have 2 failures, that is not a binomial distribution. That is a different sort of distribution. It might be negative binomial. And then a second thing to keep aware of is the independence. And if independence is not a real life situation you're dealing with, then you can't be using binomial. Any last questions about binomial? Okay. Okay, so let's talk about another distribution, Poisson. And one way to introduce you to the Poisson distribution is suppose we have something that's binomial, but n is really, 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 really large. But p, the chance of success is really, 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 really tiny. Large n, small p. Okay. So, like winning the lottery. Winning the lottery sounds like that. There's a large number of people who play, but the chance that any one ticket is the winner is very small. Okay. If you're in a situation where essentially, okay, n is so big and p is so small that you'll either have one success or no success. More often than not, no successes. Okay. You're going to have the distribution. Darn it, that's a 4. Okay, bail. Okay, so I'm just going to say large and small p is binomial, but there are other things as Poisson, but large and small p binomial is Poisson, but there are other ways to get the Poisson distribution. Okay, so here's another way to get towards the Poisson distribution. So what if we have time between calls into a call center? Okay. And so it's during the peak of the day when calls are likely coming in fairly quickly, rather than in the middle of the night when few people are making calls into the call center. If we know that the distribution between the times into the call center follows an exponential distribution, okay, and then keep track of the number of actual calls in any given 1 unit. Damn it. Okay, head spinning. Okay, so start slow. I'll go slower. So if we have the time between calls, and if that's y, is just to be exponential with parameter lambda. And so we talked yesterday about the exponential distribution, and that says f of y looks like that. So in other words, as y gets larger, the chance that we hit that is really small, okay? And so if what we're saying is the time between consecutive calls follows this exponential distribution, most often it seems like you're going to have another call right quick. But every so often, rarely, you'll have a very long time until that next call, okay? And so as we have the calls coming into this call center, it's going to be typically, and if we have as time goes by. Okay, so we're starting here at 0. Then we get a couple calls right there because, you know, they're well, not much time in between the calls. Okay, sometimes you wait a long time. Sometimes you wait a very long time. And if we take our time and then keep track of the number of calls per unit, and let's say this is 1 minute, here's another minute, here's a third minute, there's a fourth minute. And if X here, X is just the number of calls in a minute. So in this case, X looks like it'd be 1, 2, 3, 4, 5, 6, 7. Here, X would be 4. Here, X would be 4. Here, X would be 2. Okay. Now, if that is the way our data are arriving, okay, the calls coming in, you would say then that the number of calls per minute follows an the time between consecutive calls would follow an exponential distribution, but the number of calls per minute would follow a Poisson distribution. So let's talk about the Poisson distribution. So if X is distributed Poisson with parameter lambda, POI for Poisson, we would say then the probability that X is equal to lowercase x, a particular possible value, or P of X, that's the PMF, is going to be just e to the minus lambda e to the minus lambda, okay, times lambda to the x power over x factorial. So that's for x equals 0, 1, 2, positive or non-negative integers, and 0 elsewhere otherwise. Okay. So I guess if I tell you the value of lambda, okay, and then I could ask you about the chance of any particular outcome, I think we could solve for that probability. So let's try, if lambda is 1.75, right? Okay, probability that x is 0 would just be e to the minus 1.75 times 1.75 raised to the power 0 over 0 factorial. And those last two terms sort of drop off because, well, you know, math. So just cancel those out. There we go. And we have just e to the minus 1.75. And I don't know what that is off the top of my head, but you could tell me.
It's 0.174.
Okay, so 0.174 is the chance of 0 successes or 0 events in that 1 minute time period. If you want to know the chance of exactly 2 successes or 2 events in that time period, we're going to plug and chug the same way. E to the minus 0.175 or 1.75, 1.75 squared over then 2 factorial or 2 factorial. And that's going to be, well, so same thing, e to the minus 1.75 times 1.75 squared over 2. And that would be, not the same, smaller. The number itself would be helpful, though.
I'm like getting a larger one, that's why.
Okay,
Maybe
so, oh, yeah, it would be larger. Yes, I'm sorry. It would be larger, definitely.
I got 0.266.
266. Yeah, I was looking, and maybe let's highlight where I was looking right there. I was thinking, oh, 2, and then upstairs we get a 1.75 squared, and I was not remembering the 1.75 squared would be larger than 2. So here we got another example. Okay, so Poisson problems, not too bad. Let's try a different question, and let's try with well, the same setup maybe, lambda 0.175. So let's write that down. Lambda is 1.75. Okay, And what if we want to find the chance of at least 2? So if what if you want to find the chance that the outcome x is at least 2? I guess I could write that as the chance of 2 plus the chance of 3 plus the chance of 4 plus, and then I could go on forever, and that would take a long time. And ultimately, I will run out of patience. Okay, but those numbers are going to be small, but then I can't really ignore them because, calculus type things. I'm thinking there's got to be a cleverer way to tackle this. And the cleverer way is to note that in a discrete distribution, the chance of all of the possible outcomes sums to 1. Okay, so the probability of at least 2 is equal to 1 minus the chance of less than 2. And I think this is a time it's worth pointing out that at least 2 and less than 2 are logical opposites. And with discrete variables, it's really important that you keep track of logical opposites, to use this 1 minus approach. At least 2 means 2 or more. The opposite of that is strictly less than 2. Okay, so you can now solve, because this is 1 minus p of 0 plus p of 1. That's the chance of 0 or 1. And if I remember that this would be 1 minus, what do we have? Well, we solved for one of these earlier. What did we get earlier? I erased that. 0.17.
0.174.
74. Let's write in the chance of 1 here. So e to the minus 1.75 times 1.75 over 1 factorial. Okay, so that's just 1.75 times 1.74. So that is the sum, and the ultimate difference is solvable.
I got 0.522.
Sounds plausible. I like it. Okay, so what I want to do is move forward into the relationship between Poisson and binomial. And this is something I was hinting at earlier, but I didn't sort of want to pursue that line because it was a brain fart. Okay, so for if x is distributed binomial, NP, and n is big and p is small, and those are two relative terms, big and small. I usually think big's like, well, shoot, n big, p small. And if and we're just going to say lambda is equal to n times p is also small. Okay, so I'm thinking big here. Let's change colors to emphasize big. Greater than or equal to 50. And lambda n times p is less than or equal to, say, 5. Now, those are rules of thumb. Those are approximate, and those will bail out in some situations, depending on how precise you want to be. But here is an approximation. You'd say if we have a binomial with very large n, very small p, sometimes the calculator won't do the binomial calculation, but you could do it with Poisson. Okay, so let's go ahead and note that the probability that x is equal to lowercase x, we would write that that's approximately, maybe let's do this better, approximately e to the minus lambda, lambda to the x over x factorial. Okay, so as an example, let's try something that's binomial, but we couldn't easily solve it. So if n is 10,000 and p is 1 over 10,000, okay, what is the probability that x is exactly 2? Okay, so if I tried to use the binomial approach, I would end up with 10,000 factorial over then 2 factorial. Actually, let's go with not 2. Let's go with 8. Eight factorial and then 10,000 minus 8. Yeah, minus 8 factorial over 1 in 1,000 or 1 in 10,000 to the 8th power times 1 minus 1 in 1,000 or 1 in 10,000 to the 10,000 minus 8 power. I believe probably some of you have calculators that could do this. The calculator I have, which is old and only 8-digit precision, can't. Sorry. I will say though that in your life you'll bump into problems every so often where you're not going to be able to pull off this question very, very easily, and it might be due to my choice of 8 here. But have you tried 10,000 factorial on your calculator? 10,000 factorial on the calculator is not your friend. Okay, so we could say I can't solve the problem. I cannot solve the problem, but you can approximate an answer. So I'm going to switch gears and use the approximate solution here, and I'm going to switch over to red and maybe eliminate that here so I have room to work. Okay, so with this red color here, I'm going to say, okay, all I need to know is n times p, and n times p is, well, 10,000 times 1 over 10,000. Lambda here is just 1. So I'm going to e to the minus 1, and then lambda, which is just 1 to the 8th power, over 8 factorial. Okay, so that's relatively easy to calculate, rather quick to get. E to the minus 1 over 8 factorial. Now, it's a small number, but we could basically find pretty quickly that chance exactly. Okay? Any questions about how to do that? Okay. So what I'm going to do here is switch gears and note that if x is binomial, we can also sometimes use the normal curve to approximately get answers. And I'm thinking, well, computers, we could get exact answers. Sure. But the reason we like to use sometimes these approximations, like a normal to approximate a binomial, is it gives you a sense of gut feeling for what the answer is you're likely to get in any given situation. Okay, so let's go ahead and start on the normal approximation to the binomial distribution. So the normal approximation to the binomial distribution. So if x is distributed binomial with n and p as the number of 6 trials and the chance of success, and if n times p is greater than or equal to 10, and n times 1 minus p is also at least 10. And I'm going to say over here, I've seen other books where they say, oh, no, you need it at least 5. The larger n times p and n times 1 minus p, the better the normal approximation to the binomial actually is. Okay, so let's go ahead and talk about that normal approximation. The probability, if x is binomial np, the probability that x is less than or equal to a is a constant, and I'm being very careful here. Okay, less than or equal to. So A is an integer. Okay, so this would be the probability that X is 0 plus the chance that X is 1 plus the chance that X is 2, all the way up to the chance that X is exactly lowercase a. Okay. Well, I think we can approximate that with the normal CDF as long as I remember that the central value is just n times p. And so let's try and convince you of that in a quick way. If you're flipping a coin 100 times, and if it's a fair coin, about how many heads would you expect to see? 50? What if I'm going to roll a die 600 times? About how many ones would I expect to see? 1/6 of the 600 or 100. So the number of trials times the rate of success should give us the average number of occurrences. So if mu is n times p and sigma is gonna, for reasons that a different class goes into, but this one does not, it's the root of n times p times 1 minus p. That's actually from the Bernoulli distribution and building it up. And in office hours, we can talk about proving this if you'd like to. I'm thinking this is not the proof class, but if you happen to know n and p, you could get mu and sigma. Okay. And the chance that X is less than or equal to A is approximately equal to, so I'll switch colors for the approximation, is approximately equal to the normal CDF value of A plus 1/2 minus mu over then sigma. So let's try a problem, and this is going to be fairly straightforward, and we'll do it with flipping coins. So if I'm going to flip a coin 100 times, and if it's a fair coin, and that's always a radical thing, fair coin, what's the chance of 43 or fewer heads? Okay, so if, okay, there we go. So if n is 100, and if it's a fair coin, the chance of a head is 1/2, 1.5. Probability that X is less than or equal to 43 heads in 100 flips of the coin. We could solve. I mean, literally, I could with JMP's probability distribution calculator. I could say normal. No, I could say binomial and n and p and add it all up. Or you could do it by hand and add it all up. You could add up all of those things, each of which has a factorial in it, or 3 factorials in it. I wouldn't want to do that. Okay. Or I could just approximate the answer. Okay. So let's talk our way through how you would do the approximation, and then we'll get to the obvious question before we close for the day. Let's erase some stuff upstairs. Okay, now I'm going to erase. Okay. Okay, I'm not able to erase. Okay, great. Okay, so let's just move forward. You know what? This is what happened yesterday or 2 days ago, isn't it? Okay, so I'm going to leave, rejoin, and then we're all good. I'm very annoyed by this feature. Okay, and then, oh, I had to also stop the share and restart. Now, resharing again. Okay, so let me just start where we were here, and we had an N of 100 trials, fair coin, so 1/2 is the chance of a heads. and we want to find the chance of 43 or fewer heads in 100 flips of the coin. Okay. Okay. So we could solve for that. Again, we could find the probability of 0 and 1 and 2 and 3, and those are already pretty small, but you would eventually, it's a lot of work. Okay. So we're claiming that that's approximately equal to the normal CDF of 43 plus 1/2 minus mu over then sigma. And in this case, mu we know is n times p, here 100 times 1/2 or 50. And sigma is the root of n times p times 1 minus p. So that's the root of 100 times the root of 1/2 times the root of 1/2. Okay, so that's 10 times 1/2, that's 5. So we say this is cap phi of 43.5 minus 50 over 5. Okay. And I guess I could solve this, but this is sort of hard for me to do in my head right now. Cap phi of negative 1 point what? 1 and 1 point, negative 1.3. Hey, could you check my math here? In my head, I'm not mathing. 43.5 minus 50 over 5.
Negative 1.3.
Okay, so I did get it right. I'm very proud of myself. Okay, so I happen to now have, well, come on, GMP's probability distribution calculator. Darn it, try to get over into the corner here. But if I put in my fun little number, negative 1.3, it will tell me 9.68% or 0.0968. Again, I did suggest earlier, if you did say binomial, okay, and you had p of 6 as 0.5 and 100 as the number of trials, okay, we could reset the distribution there, and the chance of binomial input quantities and calculate lowercase area for what do we say, 43? No, hold on a second, that's very wrong. N should be 100 here. Okay, and now 43. Okay, so 0.0967 relative to the 0.0968. Yeah, we're pretty close. And you can even see that this binomial distribution in shape is about the same as a normal distribution in shape. Okay, so not a bad thing to do. Setting you up for the lab, same lab groups today as yesterday, or as like last time. The lab today asks you to consider the Poisson distribution and a normal approximation to the Poisson distribution. You get to figure out under what circumstances things are really good as far as approximations go, and in what situations maybe not so good. But yeah, the normal curve could be used to approximate a Poisson distribution as well, but only sometimes. Okay, so that's it for what I had prepped for you for the day. Hopefully things are going well in your life, and hopefully I'll be better by next week. Right now I'm still with the head spinning, but you know what? I'm at least upright. Any last questions before we call it a day?
I have some questions about
Sure.
like my DRC stuff, but that's
Okay, well, hold on a second. What I'm going to do is I'm going to stop the recording and